want to say good afternoon to everyone and thank everyone that came before me for their presentations. They were all very interesting, and I'll try not to take too long because I'm sure everyone's ready to get home. But like Judy said, some of you might be here expecting the presentation, which was rating poor condition bridges in BrR. And basically, I had a miscommunication, and we were considering two presentations for this slot, and I told Judy I was doing one, and then when I got to working on it a little while later, I did the other one because I got confused. So the presentation I have today is about moving very heavy superloads and using BrR, and it's just sort of it's not a highly technical presentation. It's more of an overview of some of considerations we've run into and ways we've used BrR, and also sort of why I think BrR is an excellent tool for this, and this is one of the best uses for it, one of the biggest positives about the program that I've found. So to get, So to get started, we deal with a lot of super loads in Louisiana, and engineering review of these loads is a major part of the work we do. Second only to actual rating. Analysis of these loads is also very technically and man-hour intensive compared to certain other things. And it's also very important because movements of these loads are a very important part of our state's economic engine. The oil and gas industry is very big in Louisiana. And just as evidence of this, there's a town near where the bridge which we've had the most heavy loads passed, and the name of the town is Norco, which is simply an abbreviation for New Orleans Refinery Corporation. So when they're naming towns after the refinery, you can tell that this is something pretty important to the state. These are just some pictures of super loads, and you can see most of these are made for the chemical industry. The first one, you can see, interestingly, it is moving diagonally across the bridge, which is something they call crabbing. I think this is one of the first times we did that recently. We did that for the first time. So. And this just shows you can get a scale from the people to see how big these loads are and how much they take up the entire bridge. And it gives you an idea of how there's not a lot of room for error when you're dealing with loads that are this heavy. We officially consider anything that weighs more than 254,000 pounds a superload, but for the sake of the presentation I'm giving today and what we're talking about, I'm focusing on loads that are closer to 1 million pounds gross vehicle weight or even greater. 1 million kips, I'm sorry. It's 10 times greater than the legal load for most of our bridges. The transverse width of the vehicles are greater than the 6 feet, which we assume as a wheelbase for design trucks. And obviously, I'm sure a lot of you are familiar with this, and this is what causes a lot of the complication in the analysis of these vehicles. It's also what allows them to move at such huge weights. The wheelbases we typically deal with on very heavy loads is between 16 and 34 feet. And we have super loads, and those bring super challenges with them. The first one is typical bridge engineering challenge based on the unusually heavy loads and situations. The other issue we have to deal with is that projects in the oil and gas business move very fast, they change regularly, and they involve a lot of money. Also, conditions in the field for fast-moving complex projects are dynamic, and our assumptions can change drastically. And mainly what this means is things like, does the vehicle that's moving actually match the weights on the vehicle that was submitted to us? And I find that BrR provides a great tool to meet these challenges, and mainly because once you have the bridge modeled, you can run non-standard gauge analysis, and unless the bridge is really complicated, you can do it in a matter of minutes. And it spits out pass or fail numbers. And if things change, you can do this even on a laptop at the load site, which we've done before. The weights on the trailer come in different. You can simply plug that in and run that, and in a short period of time, you can have reanalyzed instead of because it's just not feasible to tell people who are moving these heavy loads that are waiting on the side of the road that I'll get back to you next week after I've rerun tons of fancy finite element models and etc. And so BrR is a tool that works for these situations. The considerations we usually deal with is live load distribution, which is the main issue, actual bridge behavior versus assumed bridge behavior, actual load configuration versus reported. And again, in this case, I don't think that BrR necessarily does anything that you couldn't get done with some combination of other software packages, but it does it very quickly and with the least amount of input on our part. It allows us to move fast to review permit applications, and this is very important for the customer. Time is money, and for us, minimize traffic interruptions or job security. And we've even have loads where they've pulled over in parking lots on the side of the road, or sometimes still in the road, and to have to wait multiple days to reanalyze something that weighs different than you thought it was is just doesn't work for that situation. So as far as live load distribution, when you're looking at permit loads, you have a couple different choices. One is to simply use the prescribed equations in the code for the designing legal load rating. The pros for this is there's no extra work and you have a high assurance of safety. There's a long history of designing bridges by the code, and so you have a lot supporting that it's going to be safe. The cons is it's extremely conservative to the point that it unnecessarily restricts loads in a way that's damaging to our state's economy. And this would not be a possible feasible approach for us. They're just simply the businesses are too important. Live load distribution factor 2, and this is something that was more popular when I first started doing it, is what I would call back of the envelope load distribution calculations. This is sort of different tricks that people have used in the past to come up with distributions of trucks that are different than the 6 feet width. Some people do it by ratios. Some people use certain versions of the Weber rule. Some people consider the deck a continuous beam. There's a lot of different type of methods that we used back in the day. And the pros is it's simple and it works reasonably fast. It gives you a little more room than just using the code design legal distribution. The cons are it can still be very conservative and it provides less safety. These methods, although a lot of times they have some sort of rational basis to them, they're not usually, if you went to talk to 4 or 5 different states, you probably get 4 or 5 different tricks or things that they do. And so it is kind of risky because you don't have academic research or years of practice supporting any one particular method. Despite all that, this was a useful tool before finite element was regularly available. But now with BrR and non-standard gauge, this is not something we really have to worry about anymore. And the last is load distribution with finite element. And this is the picture is of a third-party analysis we did one time. But it provides accurate modeling of bridge behavior and load distribution, and it's a verified method. The downsides of this is it requires a high level of technical proficiency and experience. These methods tend to be sometimes a little bit black boxy, and if you don't have people that know what they're doing, it's easy to get into trouble doing this. It's also very labor intensive if you don't already have models built. It takes a long time to build them, verify them. You also need to experience or to purchase expensive software and invest significant resources in training your staff. And another issue is that we've always had with using commercial finite element packages for this is, and this is changing some, but in the past, a lot of these programs spit out results that were in forces or stresses, and you had to do another step further to get that into sort of a pass-fail type situation. And so one of the things we really like about BrR and non-standard gauges, we feel it gives us a lot of the advantages without any of the negatives. So the number one advantage is you already own it. So assuming you already own it for your regular bridge rating stuff, there's no additional marginal cost to it. You and your staff already know how to use it. There is maybe a little bit additional information you need to use the non-standard gauge functionality if you're not experienced using it, but it's very little. And all the girder bridges you have modeled in girder system are automatically modeled in finite element. There are some exceptions to this, of course, but the vast majority of them. And when you run it, it spits out rating factors, which are pass-fail decisions ready for you to, I don't have to further refine the results I get from it. And another thing, and it seems like maybe not a huge deal, but this has been very important to us, is the fact that you have a library of all the old loads that you've analyzed, assuming you're keeping them. And that's in the database. And when we're moving loads that are as heavy as the ones that we're talking about here, we want every bit of information we can have to give us some confidence that we're not going to, have a problem. And being able to run old loads that we've passed on the bridge before and compare those numbers basically in the same analysis with the new truck that's been submitted, without doing any extra work to do any of that, that's incredibly useful. So the main thing we use here in BrR is distribution factor line girder. I think a lot of you are probably familiar with this, but maybe there's some states that don't use BrR so much for permits. So if you don't use this, it's something that I would encourage you to look into because it's very useful. And you can do a lot of customization. You can put in vehicle step size, whether you want to travel centered to the left or to the right, or you can also put in your own user-defined load path of where you want the truck to travel on the bridge. And you have these settings that can affect, how the finite element model is built underneath the hood. And these are some typical settings we just usually use. I've always been told to keep the number of shell between elements to 3 or above. We like to use 4, and to keep the aspect ratio to 2 or less. So these are settings we use, and most bridges, with the possible exception of a bridge that has many continuous spans, most bridges run relatively quickly like this, less than 10 minutes. And this is just a screenshot of where you input the vehicle, and I'm trying to show that you can have different axles for different configurations for every different axle on a truck. And this, it also uses the wheel width. And I guess the only one thing I'd like to see us improve over time is the way this works. This input screen can be a bit confusing. It'd be nice if you could see the schematic while you're inputting, but anyway. So the benefits to having this functionality really add up when you are analyzing these permits and trying to get them passed. And in the past, when I first started working at the DOT in Louisiana, any move of over 60 miles for a superload was not allowed unless there was no other options. People had to ship it or send it by rail to as close as they possibly could get it to wherever they were going before they could put it on the highway on a truck. But based on economic and political pressure, sometime in the 2000s, this changed. And now we see very heavy loads that move all the way across our state. The significance of this is that we found that when we had this restriction in place, if someone was moving a very heavy load, or even a load that's only 500,000, they usually would cross one bridge, which really limits the amount of work you do. And so then modeling that in some other finite element program and analyzing it that way is more time consuming, but not totally out of the question. But when we regularly have loads that require refined analysis on 10 plus bridges. And without BrR, which is able, as long as you have the bridge and girder system and you've done a good job of modeling it, without any additional modeling that you have to do, you can run this non-standard gauge analysis and on any bridge that you have modeled that way. And you know, to look at one bridge in a finite element program, like I said, it could be potentially doable, but to have to do that for 10 bridges for a load that you have to turn around in 2 weeks or less, that's basically impossible. And so without BrR, the cost of money and time would be astronomical, and we wouldn't be able to do it, and we would be stuck either having to make a lot of assumptions and letting a lot of things go that we weren't 100% sure about, or we would have to reject loads that we really didn't need to reject. So BrR in the permitting process, just for what's on this one slide, has been a huge deal for us. We've also done load testing to verify how BrR models work, and this is just some pictures from one project we did where we tested loads. The significance of this is that after we tested, we compared to what we were getting in BrR, and we got pretty good numbers. And then we also, to some degree, have been able to refine models we have in BrR with the information we've gotten from load testing to give us better numbers in the future. So these are just pictures of typical strain gauges used in load testing, and a picture of another overload. And so this is the measured versus predicted numbers we got. And, you know, we're pretty close, and that's pretty good, especially compared to, you know, this is measured, you know, actually what loads we actually measured and what we predicted were, you know, within 5%. And so those numbers are very good. This is just one example from a project we did. I pulled that out of the files when I was doing the presentation, but we've had several, and the results are always somewhat similar to this. So I feel like, and I think we as an office feel like, we have a good level of confidence that we're getting good numbers out of this. We've also done a lot of comparisons of what we get from BrR to other finite element packages where we could, and the numbers are pretty consistent. So we feel like it's a pretty quality, you know, it's something that we can feel very comfortable using. So like I said, we can refine our models based on load testing to give even better results. This is something that you don't have as much flexibility to do this in BrR, depending really on the bridge type also, as you would in other programs, but you can do some of it, changing material properties and also the end conditions, the support conditions. And so, so there is some ability to do that. Just for the move we showed with the load testing, it had multiple bridges on it, and it involved 20 plus configuration changes before we found a solution that worked. And again, to have to run so many different loads in a bunch of models in some of the other programs we've used would have been a ton of work, and it's virtually no, you know, it's five extra minutes in BrR. So analyzing all the configurations and comparing these ratings to multiple former loads that had safely crossed bridges was only possible using BrR as a tool. Another issue that we've noticed, and this is something that came about from load testing, actually, that we did several years ago. Some of the people that did load testing for us came back, when we were poring over the results and looking at what information could we get from it, and what that could tell us about loads in the future and our whole process. We found out that that they were able to tell us that we weren't able to determine that certain vehicles weighed more the total vehicle weight, but we were able to tell that there was, in some cases, a pretty significant difference between axle groups and what they weighed. And if you look at the schematics for these loads, that's not supposed to be the case. They're supposed to all weigh the same. And so that's something that we became very concerned about, because again, with these big loads, any inaccuracy becomes a much more important than it would be if you were dealing with a load that was 10 kips over the legal weight, because you're already running so close to the edge of what the bridge's capacity that you don't have room. There's not nearly the wiggle room, if you will. So we always were interested in getting some of these loads weighed, but we weren't able to do it because of size limitations of the scale. So one thing we did is around 2015, we purchased our own scales and we started to weigh many of these loads. So there you see a typical scale, and here's some of the stuff we move. So obviously that's not going to work. And this is why for so many years people didn't weigh these vehicles. And if you don't have some sort of special measuring, scales or whatever like we have, there's no way to measure these, and you have to basically run on faith. And so this shows we have, I believe, 8 scales, and this just shows one of the trucks that we've moved, and it's moving over the scale. We weigh each axle and each tire. And again, we find that when they load these things onto ships and take them off ships, most of these are shipped from overseas. They're fabricated overseas and shipped to the Mississippi River and basically driven into the refineries. When they take them off the ships and put them on the ships, they have cranes that weigh them. So the gross weight of the vessel is usually fairly accurate, and the haulers usually know their equipment pretty well. So the total weight of what the vehicle is, they know very well. But there is a lot of question of how the weight is from axle to axle to axle. Whenever they submit these things, they'll tell you that every single one of these axles and every tire all carries equal weight. And in some cases that's pretty true, and in other cases it's not 100% true. Although we have found that, especially now that they know that we will weigh them sometimes, we found that they do a pretty good job of this. This is just another picture of our scales and the tire on there. And the clock is ticking. So this, for instance, these guys, they needed to move all these in a short period of time. We had another one where they had a certain setup of these hauling machines that they carried the weight on and the load on, and whenever they got to the bridges they needed to cross, they had a different set of hauling vehicles that they used for the bridges, and they basically just pulled over in someone's parking lot and switched it out, and then we had to weigh it on site there. And the thing where BrR has come in, this part seems like it's not that related to BrR, but actually BrR has been very important to us, because overall the numbers on their axles have been decent, but sometimes they're enough different that we have to check again. And because of how easily BrR is set up and how quickly it can be run, we can modify a vehicle with a magnification factor, or go in and change the actual loads on various tires and axles. We could have every single tire and if you wanted to, you could input it to where every single tire on that truck weighed something different. And then you can immediately rerun it. And so we have a good idea of that we're still okay when some of the axles and some of the axles and some of the tires come in weighing heavy. And like I said, when these people are waiting to move these 3 vessels, or when someone's pulled over on the side of the road switching out trailers, you can't weigh it, find out they're a little heavy, and tell them you'll get back to them next week. You need an answer right away, and BrR has been indispensable in being able to do that. I've had times where we've actually rerun files on a laptop on a site like this. There's been another time where I've been sitting in the office and someone's been phoning into me what the axles weigh, so we can immediately turn around and figure out that yes, we're okay if he's still moving. And it would be really hard. I think we feel like we have a really good, a much higher degree of safety than we did in the past because we're able to weigh some of these loads. And it would be impossible for us to do that if we didn't have something that we could have that where we could turn that information around right away. And like I said, this can be done in the field on an average laptop as long as you have your BrR's data on, BrR data on the laptop. So in conclusion, superload permitting is very important to us, and I would imagine it is to any bridge owner. It may be slightly more of an issue to us because we have the southern part of our state is so industrial, and maybe we see a little more frequent heavier loads. But I know just from presentations and things I've seen that a lot of states deal with this same thing. And BrR has allowed Louisiana to do this efficiently, and we didn't have to go out and buy new software, and we didn't have to train a bunch of people to use a new program. And we've gotten results that we verified against other programs and verified in the field, and they're very accurate. And so this gives us a tool that allows us the flexibility to protect infrastructure, have confidence that we're not going to damage our bridges, while at the same time allowing some projects that are very important to our economy go forward. And we're able to do that in in the speed that matches the requirements of the industries that we deal with.